The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay, so we were talking about the energies of the states, the various states in a multi-electron atom. And the question is, how do we know what these energies are experimentally? And the technique that we use to know those energies is something called photoelectron spectroscopy. In principle, it is the same kind of spectroscopy as when we talked about photo emission from a solid, the photoelectric effect explained by Einstein. And by the way, I put on the website an article that is really very clear about what Einstein's contributions were, in particular in explaining the photoelectric effect, and has some sociology in it too. So it's really a very easy to read article. Encourage you to take a look at it as a study break sometime. Anyway. All right, so the idea here is the same. The photoelectron spectroscopy off of atoms and molecules, same thing as the photoelectron emission from a solid, in that you send in a photon and that causes an electron to be ejected. But unlike the solid, where we essentially had just one, we just had one state at a particular energy, in an atom or a molecule, we've got many different states with many different energies. And what we typically do then is we send in a photon that will be able to ionize all of those electrons. That is, it's a photon with enough energy to rip off even the most strongly bound electron. And so that photon is typically an X-ray photon. So for example, we take this unsuspecting neon atom and we bring in an X-ray photon and make neon plus. And one of the electrons that can come off is, of course, the 2p electron here, so that the ion configuration is 1s2, 2s2, 2p5. And then, of course, another possible electron to be pulled off is that 2s electron. So the electron configuration is 1s2, 2s1, 2p6. And then finally, if the photon has enough energy, well, we can pull off the 1s electron to make the 1s1, 2s2 configuration, 2s, 2p6 configuration. And what we then do in this technique is we measure the kinetic energies of all the electrons that come off. We measure the kinetic energies and we disperse that so that we get a plot of the number of electrons with a particular kinetic energy. So the plot is what I show you here. Number of electrons versus the kinetic energy. And what you see is that we have three kinetic energies that show up. We have electrons with three different kinetic energies. We have three different kinetic energies because in neon we had three states with different energies. So for example, this here, this energy, 384 eV, that corresponds to the electrons that were pulled off, electrons that were in that 1s state. That's the most strongly bound state. So for example, if this is the energy of our incident photon, and then this is the ionization energy, which is going to be largest for the 1s electron because it's most strongly bound, well, then the energy difference between the incident energy and that ionization energy, well, that's the kinetic energy of the electron. That's the energy, the leftover energy that goes into the kinetic energy of the electron. That's going to be smallest because that 1s electron is most strongly bound. And then we have this kinetic energy here. Electrons with that kinetic energy were electrons sitting in the 2s state. That has higher kinetic energy because they're less strongly bound. So if this is the energy of the incident photon, this is the ionization energy of that 2s electron. That leftover energy then is that kinetic energy. And then finally, this is the feature that represents the electrons in the 2p state. They're least strongly bound. So if this is the incident energy, this is that ionization energy for the 2p state. All of this energy is left over to go into kinetic energy of that 2p electron moving away from the atom. Okay? And so in general here, as the kinetic energy goes up, well, the binding energy here is getting less and less negative. It's getting weaker and weaker. Or in other words, as the kinetic energy goes up, the binding energy is getting more negative in this direction. Okay? So very quickly, if you look at a photoelectron spectrum and you see three lines like this, you know you've got three states at three different energies. And you always know that the highest kinetic energy means the least strongly bound electron. The lowest kinetic energy means the most strongly bound electron. And then we can use these results to actually calculate the binding energies of the electrons, right? By conservation of energy, and this you have to know for the exam, right? Incident energy is that ionization energy, or the work function in the case of the solid, plus the kinetic energy. Or I can turn this around, right? I can solve for the ionization energy. That will be the incident energy, which is right here. This is the energy of that X-ray photon, 1,253 eV, minus the kinetic energies that we actually measure, are going to give us those ionization energies for each one of the electrons in their corresponding state. And then once we have those ionization energies, well, that's easy to turn it into a binding energy, because that ionization energy is equal to minus that binding energy. So for example, since the ionization energy, the 1s electron is 870 eV, the binding energy of that 1s electron is minus 870 eV. Okay? All right, and I also want you to know there's just how much more strongly bound that electron in the 1s state is compared to the electrons in the n equal 2 states, in the n equal 2 shell. And that's because that n equal 1 shell is much closer in to the nucleus, where that attractive interaction is much stronger. And therefore, this electron is much more strongly bound than those electrons in the n equal 2 state. Of course, 2s is lower in energy than 2p, and that's important, right? This is because in the 2s state, you have a finite probability of being really close to the nucleus, right? That's what makes that 2s a little bit lower in energy than the 2p. Great. All right, so now what we're going to do is I'm going to start lecturing about trends in the periodic table. And this is where the questions come for your section. Oh, okay. All right. Okay. Do you have any extra paper? Not much. Oh, okay. All right. Well, the way you were going to be able to answer a question for your recitation is by making a paper airplane and launching it to the blackboard after I say launch. And the first paper airplane to hit the blackboard, well, hey, you'll have that opportunity to answer the question. Your recitation will have that opportunity to answer the question. And we'll keep score. Now, we're kind of running out of extra paper. You can take the one page that asks for the seating plan that you won't need again as a piece of paper to make an airplane. Do you have any other paper? Not any. Okay. Right. You do need that. Here are a couple of extra pages. Also, if you need some, there are some paper airplanes up here. You're welcome to take those. Okay, now some of you are more strategically placed than others, and so you may want to designate someone in your recitation section as a launcher. and send them down here so that everybody gets an equal chance. That's fine with me. Okay? And as I said, if anybody wants some paper, oh, also the other thing, write your recitation section number on the airplane so that I can identify which airplane and what section it comes from. And they have to be airplanes. They can't be wads. And here are some extra airplanes if you want. You can take some and pass them back if you want. Okay. So while you're doing that, I'm going to start lecturing here about trends in the periodic table. And of course, it's these electron configurations that allow us to understand the trends in the periodic table. But you should realize that the periodic table was initially put together by Mendeleev and others in the 1850, 1870. And it was put together on the basis of the similarity of the chemical and physical properties of the elements. So for example, you know, lithium, sodium, potassium, they were put in the same column because those elements are all soft, malleable elements that were very reactive. You know, helium, neon, argon were put in the same column because they're all atoms that are very unreactive. And of course, today we understand why their properties are what they are, and we understand it on the basis of the electron configurations. In lithium, sodium, potassium, we have this extra valence electron in the S state that makes it very reactive. Helium, neon, argon are very unreactive because they have this closed shell, this inert gas configuration. But really, by the late 1800s and early 1900s, the similar chemical properties as you go down a column of the periodic table was really very firmly believed, to an extreme extent. So strongly that it was known that, of course, human beings ate salt and that the bodies had sodium ions in it and potassium ions in it. So, hey, if that's the case, if you can consume sodium and potassium, why not a little lithium? All right. So in 1925 or so, there was marketed a soft drink. And this soft drink wanted a lemon lime flavor to it. So to get that lemon lime flavor, they needed a little bit of citric acid. But that's not very soluble in water. So to make it soluble, you make it a salt. And for whatever reason, they used lithium citrate. Hey, why not? Let's use some lithium citrate. And that soft drink was none other than 7-Up. Honestly. And in fact, it was the benefits of lithium were touted. Right? Lithium was claimed to give the beverage healthful benefits, an abundance of energy, enthusiasm, clear complexion, lustrous hair, lustrous eyes, shining eyes. Hey, gotta drink this stuff. So it was on the market for 25 years until the early 1950s when the antipsychotic properties of lithium were beginning to be noticed along with the severe side effects of lithium. And it was then taken off the market, or at least taken off the market as with the citrate as the lithium salt in it. And it really was only, you know, another 20 years, 1970, before lithium was actually approved as a drug for the treatment of antipsychotic behavior. So, you know, I don't know how many individuals suffered the side effects of lithium from drinking too much 7-Up. But there is a moral to the story, and the moral, of course, is that even though we're about to talk about the general trends along a column of a periodic table. Don't put any element in your mouth just because it is in the same column of the periodic table as some element you do eat. Okay, so this is a for real story. Okay. All right, so one of the properties we're going to talk about is the ionization energy. And we've already used the word ionization energy quite a lot. But let me just formalize the definitions here. So for example, we have a boron atom being ionized. The energy difference between the products and the reactants here is that ionization energy. But this ionization energy is minus the binding energy of the 2p electron in boron. Right? That's what that ionization energy is. We're ripping off the least strongly bound electron. And when we rip off the least strongly bound electron, we call that the first ionization energy. That is the energy to remove the electron from the highest occupied atomic orbital. That's the same idea, the highest occupied atomic orbital, that's the same idea as the least strongly bound electron. All right? However, most of the time when we talk about ionization energy, we don't use the word first. If you see a list of ionization energies, if you see a table of ionization energies, they don't say first. That first is implied. All right? Now, of course, there are other kinds of ionization energies. For example, the second ionization energy. We can keep going here. We can take boron plus, rip off the next least strongly bound electron to make boron plus 2. That energy change is what we define as the second ionization energy. That second ionization energy is minus the binding energy of the 2s electron in boron plus. And we can keep going. There's a third ionization energy, taking another electron from boron plus 2 to boron plus 3. And there's a fourth ionization energy, boron plus 3 to boron plus 4. And a fifth ionization energy, boron plus 4, boron plus 5. All the way down, okay? And now we're at the bare nucleus. So that's our definition of ionization energy, second, third, fourth, and fifth. Okay, so now comes the first question. And the question is this. It's going to be on the side boards here. We've got this reaction. This is boron plus going to boron plus 2. What we're doing here is removing a 2s electron. Right? The second... Remember about the fool aiming for their chemistry professor? Look at the second reaction here. Boron to boron plus. Again, we're pulling off a 2s electron. And the question is, are these two energies equal? All right? So now, the way we're going to answer it is, after I get out of the way, I'm going to say launch. You're going to launch. And the first paper airplane to hit the blackboard, we're going to look at that recitation number, and you're going to have a chance to answer. Okay? Are you ready? Launch. Recitation 4. Are these two energies equal? That's you. Are these two energies equal? No. Final answer? Yes. They are right. 1 point for recitation 4. These energies are not equal. Why? Well, because this ionization energy is the second ionization energy. It is minus the binding energy of the 2s electron in boron plus. This energy is the ionization energy of a 2s electron in boron. It is minus the binding energy of the 2s electron in boron. They are not equal. Next question. Which one of these binding energies is greater. Okay, wait, I'm getting out of the way. Are you ready? In position, launch. Recitation 8. 8. Where are you, 8? You're over here. 8. 8 doesn't want to identify itself. All right, 8. Which one is greater, top or bottom? Top. Final answer? Boy, that wasn't wholehearted. You're right. Top one is greater. Recitation 8. It's greater because, hey, the effective charge in boron plus is larger than it is in boron. There are fewer electrons for shielding. The effective charge is larger. That binding energy is greater. All right, or that ionization energy here, the way I write it, is greater. Okay? Fantastic. Now, we're going to look at some trends in the ionization energy along the periodic table. And the first question is, here's the periodic table. As we go across the periodic table, what happens to that ionization energy? Wait. Okay, are we in position? Ready? Launch. Recitation 5. What happens to the ionization energy as you go across the periodic table? Is that 5? Is that your answer? 5?
Come on, guys.
What happens, wait a minute, what happens to the ionization energy as you go across the periodic table from here to here? Increases. You are right. Recitation 5. Okay. So here's the trend. Here's row 1 from hydrogen to helium. Here's row 2 from lithium to neon. It increases. It increases because as you go across the periodic table here, Z increases, right? The nuclear charge increases. But of course, there's another parameter here, and that's R. But as you go across the periodic table, right here, you're putting electrons into shells, into the same shell, right? Essentially. You're putting those electrons into shells that have, roughly speaking, the same distance of R from the nucleus. And so the factor that wins out is Z, right? The effective charge here. And the ionization energy as you go across then increases. All right. But you also see that there's some glitches. You see that boron is a little bit lower energy than what did I want to say here? Yeah, I'm sorry. Okay. I'm looking at it side. Okay, here's beryllium. Electron configuration of beryllium. Here it is, boron, Z equal 5. All right. All right, what you see here is that in boron, we have to put that extra electron into the 2p state, which requires some more energy. The bottom line is that the nuclear charge doesn't increase fast enough to compensate completely for the extra energy for the extra energy that you need to have to get to this 2p state. All right, so boron has a little bit lower energy, ionization energy, than beryllium. And you see another glitch. That other glitch is between nitrogen and oxygen. Well, again, we can understand that glitch by the electron configuration. So here's nitrogen, Z equals 7. Here's oxygen, Z equal 8. And the bottom line here is that in oxygen, you have to put an electron in a state in which there already is an electron. That's a repulsive interaction. And again, the increase in the nuclear charge just isn't large enough to fully compensate for that repulsive interaction. All right, so we can understand those little glitches in terms of these electron configurations. And in general here, that ionization increases as we go across the periodic table. Here's the third row. But you also see there are glitches in the third row. You see there's a glitch between magnesium and aluminum. Hey, magnesium and aluminum are right underneath beryllium and boron. A glitch between phosphorus and sulfur, they're right underneath nitrogen and oxygen. All right, for the same reason, there's a glitch at those elements in the second row. Okay? All right, now the next question is, as we go down a column of the periodic table, what happens to the ionization energy? Wait, oh boy, I look.
Disqualified.
Ready, set, launch. Five. What happens to the ionization energy? What? Decreases. You are right. Recitation 5. Why does it decrease? It decreases because. Well, it decreases because you're putting electrons into shells that are farther and farther away from the nucleus. Yes, as you go down the column, Z increases. But it doesn't increase fast enough as R increases. Remember, they're the two factors, Z and R. So although Z increases, you're putting the electrons into shells that are farther from the nucleus. Therefore, that attractive interaction does go down. The ionization energy goes down. Okay? Great. Okay, now we're going to talk about another property. That other property is called the electron affinity. So for example, if I take chlorine and I add an electron to it to make chlorine minus, there's an energy change here. That energy change, delta E, is equal to minus 349 kilojoules per mole. That is, this tells you, the fact that this energy change is negative, this tells you that the chlorine ion is more stable than the neutral atom. Okay? So now, in terms of an equation, what is the definition here of the electron affinity? Okay, that's the next question. And you ready to launch? Launch. Okay. 8, recitation 8, where are you? You're right here. No, you're right there. Recitation 8. What's the definition of the electron affinity? Hey, TAs, can't help. Energy required to add an electron. That is recitation 8. You are right. It is minus delta E. Fantastic. Great. Minus delta E. This is the delta E for the reaction. The electron affinity is minus that quantity. So the electron affinity then of chlorine is 349 kilojoules per mole. Okay. Now, unlike the ionization energy, the electron affinity can be positive or negative. So, for example, nitrogen atom. If you try to stick an electron on a nitrogen atom to make N minus, delta E for that reaction is positive. It is 7 kilojoules per mole. And so that electron isn't going to stick on to the nitrogen. All right? The electron affinity in that case is negative. It's minus 7 kilojoules per mole. All right? And again, you can understand that in terms of the electron configuration for the nitrogen. Here is the electron configuration for nitrogen. If you go and you want to add in another electron, like right there, there's a repulsive interaction, and Z equals 7. In this case, that nuclear charge isn't large enough to compensate for this repulsive interaction. So the electron affinity here is negative. Noble gases have negative electron affinities. All right, you can't add an electron to that. It's not stable. Why? Because you are destroying, in effect, the rare gas configuration of the electronic configuration of the rare gas. Okay, so with that, now what we want to ask is, how does the electron affinity change as you go across the periodic table? That's our next question. Wait. Okay, ready, set, launch. Six. Hey, 6, where are you? Hey. What happens to the electron affinity as you go across the periodic table from left to right? Decreases. Is that your final answer? Yes, you're wrong. The electron affinity as you go across increases, right? The halogens, fluorine, chlorine, have very large electron affinities because adding an electron gives you that noble gas configuration. So the electron affinity increases as you go across the periodic table. Okay, now, what happens to the electron affinity as we go down the periodic table? Hey, you guys, do you have any paper airplanes? We've got to give you some. You okay? All right, so that's our next question. What happens to the electron affinity as we go down the periodic table? Ready, set, launch. This 4. Okay. Recitation 4. What does it do as it go down? Decreases. It absolutely does. The electron affinity as you go down decreases. It decreases. It decreases because the nuclear charge here is increasing, but you're putting electrons in shells that are farther away from the nucleus. All right, so the overall effect is that R dependence dictates and the electron affinity goes down. Okay? Okay. Let me do one more here, or maybe a couple more. And now what I want to ask is about the atomic radius. Okay? Yay. What I want to know is what happens to R as you go across the periodic table. All right? I'm getting out of the way. Wait. Ready, set. I haven't said launch yet. Ready, set, go. Recitation 1. What happens to R? Decreases. It decreases. It goes down. It goes down. This is important, okay? It goes down here because Z is increasing. Z is increasing, and you're putting electrons into the same shell. And so the same shell means the same distance from the nucleus. Larger R, or larger Z, the radius actually goes down. The size goes down. Okay? And then one more question. What happens as you go down the periodic table? Hey, I'm going to get out of the way. Ready, set, go. One. It decreases. What did you say? Increases. All right. It does increase. Because you're putting electrons into shells farther and farther away. Okay, what's the score, Christine?
2 for recitation 1, 2 for recitation 4, 2 for recitation 5.
Fantastic.